So welcome everybody. Today we start with a little miracle. We will attend a Blackboard talk, and this I have not seen for such a long time. So the speaker today is David Tewodrose from Université Libre de Bruxelles, and he will talk about limits of Riemannian manifolds with a uniform Kato bound.
Okay. So first, I'd like to thank the organizers. It was quite a long time for me too. And okay, so we talk about a new class of limits of Riemannian manifolds, and that we studied with Gilles Carron from Nantes and Ilaria Mondello from Créteil. And so our main goal is to extend some known results Ricci limit spaces. Ricci limit spaces, by Ricci limit spaces, I mean limits of Riemannian manifolds with a uniform lower bound on the Ricci curvature. So we want to extend known results by Cheeger and Kolding to a larger class of limits. I'm going to start giving the definitions of Kato bounds. So let me start with taking smooth Riemannian manifolds. And number T greater than 0. Then the main quantity of this talk and of this study is this one KTMJ, which is defined as a supremum of all x in M of the integral between 0 and t of PS which minus x yes, where PS is a heat semigroup of the manifold. So if I give to PS a function f in L2, then PSF is the solution of the heat equation with initial data f. And so Ricci minus. Well, this is the negative part of the highest lower bound on the Ricci curvature. Okay, so the negative part of this quantity, you take at a given x, you take the infimum over all non-zero vectors in the tangent of M at x, of the quantity x d x. Okay. So now say that the manifold is closed. Back to the boundary. So if MJ is closed, yes.
Could you write larger letters?
Larger letters,
just for the camera.
Okay. Okay.
This is good.
Okay. So if MJ is closed, this function, Ricci minus, is a bounded function. You apply to it PS, which preserve this bound, so you get here a bounded function for uniformly bounded function, uniformly with respect to S. So what you get is that this quantity is lower than a constant times big T, and so when T goes to 0, this goes to 0. So this quantity goes to 0 if MJ is closed. So KT MJ goes to 0. And so the sequence of Riemannian manifolds we are interested in are sequences for which this quantity goes uniformly to 0. That is to say, we have some bound on the way this quantity goes to 0. So this leads me to the following definitions, and I write them here. So the sequence of closed manifolds and alpha satisfies first a uniform, what we call a uniform Kato bound. If there exists some function from, for instance, 0, 1 to infinity, such that f, the limit of f in 0 is 0. And all the quantity kt along the manifold are bounded from above by the function f. For all alpha, and have this for all t. Okay. And so we're also interested in a stronger assumption. So we add some control on f around 0. So namely, we assume that manifold, the sequence of manifolds satisfy a uniform strong bound. So in addition to this, is it okay if I write here?
Yes.
Okay. So if the integral between 0 and 1 of square root of f s by s ds is controlled by some number. So this is a technical assumption that that is useful to derive some better properties of the limit spaces. So I've just said limit spaces, but so let me just explain why these quantities ensure that such sequences admit limit spaces. So there is a result by Gilles Carron. Saying that if you have a control on this quantity kt, you can derive some modified version of the Bishop-Gromov inequality. And so this modified version of the Bishop-Gromov inequality tells you that the manifold is doubling. And so if you have a uniform control on this along a sequence, then the sequence is uniformly doubling. And so you can apply Gromov's precompactness theorem to extract convergent subsequences. So let me just write the precise statement of this Bishop-Gromov type inequality. Well, there was a first version by Gilles Carron in the paper in 2018, but so here I'm going to give a new version of the theorem in our joint work. So if MJ satisfies the following, so Kt of MJ, here it is important to take the dimension of the manifold into account. So if we have this lower than some lower than this bound, 1 by 16n for some t. Then, so then we have the following: bj of dr centered at some point x divided by r to the power n is lower than some constant theta times bj dsx by s to the power n. And you have this so for all s lower than r lower than the square root of t. And here theta depends only on n. Okay, so this gives you the doubling condition. So if the sequence of manifolds satisfy a uniform Kato bound, then there is some T uniform along the sequence for which this quantity, this assumption is true. So you have this uniform Bishop-Gromov property, and so you get doubling and then existence of limit spaces. So yeah, okay, existence of limit space. These limit spaces are pointed metric measure spaces. So here, when I said limit spaces, I said with respect to the pointed measured Gromov-Hausdorff topology, and so these spaces are proper and geodesic. By definition, then that's so we talk about Kato limits. Considering a limit space of manifolds satisfying the Kato bound and strong Kato limit. It's manifold satisfying okay. So now, why studying these spaces? Why are they interesting? So first, yes, I've erased the quantity KT, but so if you consider manifolds with non-negative Ricci curvature, so if you have this property, then the negative part of the Ricci curvature is 0. And so the sequence satisfies a trivial strong Kato bound. Okay. So in this sense, we are considering limits that are more general than limits of manifolds with non-negative Ricci curvature. And so if you want to consider manifolds with a lower bound on the Ricci curvature, then you replace Ricci minus with Ricci minus 8. Use the trivial strong Kato bound. Okay, and but moreover, so some people have already worked on more general limit spaces, so limits of Riemannian manifolds where the Ricci curvature satisfied a uniform LP bound. And it turns out that if we consider such sequence, then this sequence satisfies also the strong, the uniform strong Kato bound. So this context is even more general than the context of manifolds with of sequences with a uniform LP bound. So let me give the precise statement, which is derived from paper by Rose and Stallman. So for any p greater than n by 2, there exists some epsilon depending on n and p positive, such that if the sequence of manifolds satisfies this Lp bound, mean value alpha of Lp of Ricci minus implies a strong Kato bound along the sequence. Okay, so now I should mention that this Kato bound.
Reed, can I ask you a question?
Yes, sure.
Andrea Mondino. It's regarding the lower bound with a negative constant. So, in case your manifold is not compact, does it enter in your framework or not?
So no. I mean, not that we know. So we have only worked with closed Riemannian manifolds. And in fact, to derive the Bishop-Gromov inequality, we rely on the closeness assumption. So yeah, we don't know yet how to handle a non-compact manifold.
Okay, thank you.
Okay, so yeah, I was about to say that the Kato condition comes from the study of Schrödinger operators in Rn. So operators of this form. As B, so what B is a measurable function in Rn, positive measurable function. And so the question Kato tackled in his paper in 1923 was the uniqueness of a self-adjoint extension of such an operator. And so he gave a condition which would be at the limit when he goes to 0 of what, okay, let me write it this way. Of the integral between 0 and t of, so the Euclidean heat flow, so convolution with the Euclidean heat-kernel, the Euclidean Gaussian heat-kernel applied to V. If this limit is 0, then unique self-adjoint extension for this Schrödinger operator. Extension. And so in our case, on Riemannian manifolds, we're studying the case where V is the negative part of Ricci. And so this has already been studied in the past, especially by Batu-Neizu, who wrote an entire book on the topic of consequences of this Kato bounds on fixed Riemannian manifolds. And so I already mentioned the paper by Carron. Again, it was on fixed Riemannian manifolds. Okay. So yeah, now let me come to our main results. So before that, just to recall, just in case, so the difference between the non-collapsed and collapsed situation when studying a sequence of Riemannian manifolds. So we call the non-collapsed assumption. So you're assuming that on each Riemannian manifold, you can find point O alpha, such that the volume of the unit ball centered at O alpha is controlled by some given constant V, which does not depend on alpha. Okay, so if you have you're fine with the measure. And in case of the collapse, so in case this quantity goes to 0 as alpha goes to infinity, so we used to renormalize the measures. So we use, instead of Vj alpha, we use the measures Vj alpha, find like V as Vj alpha divided by the measure of the ball centered at O alpha. Okay, so this gives us two different cases, and so I'm going to be the two different theorems. Okay, so the first one. The first one is about Kato-limit spaces. So let's use a Kato-limit space, possibly collapsed. So then we have the following. First thing, so on each approximation, okay, so okay, maybe just I use the same notations as I've used since the beginning of this talk. So the approximating manifold I write them like this. So the Dirichlet energy on the manifolds converge in the Moscow sense to a natural replacement of the Dirichlet energy on metric measure space, which is called the Cheeger energy. Okay, so the Moscow convergence of these energies says that the spectral properties are preserved through the convergence. So you write this. So the Dirichlet energies so the Moscow converge your energy of the Kato-limit. So I will not recall the definition of the Cheeger energy, just keep in mind that it's a natural replacement of the Dirichlet energy in this context. So, in particular, this tells us that if the limit space is compact, then the eigenvalues of the Laplacian on the approximating manifolds converge to the eigenvalues of the limit space. Okay, and the second point, so any tangent cone on X nu is RTD 0n. So this means that in a synthetic sense, Ricci curvature on the tangent cone of X is positive. So maybe I should just record just in case that so tangent cones, so that the terminology is a bit misleading because so tangent cones are replacement of the tangent space for doubling spaces, and so they are not always cones. And one of the interests in the study of limit spaces is to prove that they are real metric cones. Okay, so tangent cones. I will use this notation. So the set of tangent cones at a given point small x of big X. So these are pointed measure Gromov-Hausdorff limit points. As R goes to 0, for the rescalings, R to the power -1 E. X.
There's a question on the chat, and what is Moscow convergence? Is gamma convergence?
Yeah, it's yes, it's the gamma convergence for Dirichlet forms. Yeah. So you need to check two assumptions: one assumption with a lim and one assumption with a lim sup. And, yeah. So Dirichlet energies are particular instances of quadratic forms, and so. Yeah, so I mean, what is hidden in this statement is also that the Cheeger energy of this space is indeed a quadratic form. Okay. Okay, and now, so okay, I want to keep this talk a reasonable size, so you stop here. And so the second theorem is about non-collapsed strong Kato-limit spaces, and in this case we can get even more results on the structure. Let X U be a non-collapsed strong Kato-limit. So then the first point is that any tangent cone is a metric measure cone. Okay, and any tangent cone is a metric measure cone. Yeah. Yeah, sorry, my letters are becoming shorter and shorter as so any cone is metric measure cone. So this means that you can write the measure as the measure on on a cone over a metric measure space. You can write the measure as a cone over a measured space, and you can also write the metric as a metric of a cone over a metric space. Okay. And so yeah, so this is the first point. So the second point is that so we have a similar statement. I mean, not yeah, we have volume convergence à la Kolding. So this is a result that was recalled by Daniel Semola. So the volume of balls, if you take a fixed ball, then the volume of balls converging to a ball in the metric space, they converge to the measure of the ball, the limit ball. And so there is a notion of convergence of points through the method of convergence, and this is what we use here. And in particular, the limit measure mu on a non-collapsed strong Kato limit is unique, and it is the Hausdorff measure of dimension n. Okay, so mu measure of dimension n. Okay, so now third statement. So So as I said, tangent cones are kind of replacement of tangent space for non-smooth metric spaces. But of course, if you get points where there is a unique tangent cone which is Rn, you're happy because it's like it's a regular point, like on manifold. And in fact, the set of regular points here has full measure on the space. In the space, so the set of regular points. Set of points. So that unique tangent cone that you obtain is Rn. Just a technical comment here. It's Rn with the Euclidean distance and the Hausdorff measure. Okay, it's really the Hausdorff measure. It's not a coefficient. There's no coefficient depending on x in front.
Okay. Is it unique? So if the tangent cone is Rn, all tangent cones are Rn at the point? Or is it in the definition?
I mean, this is in the definition. Okay. Yes, this is the definition of regular space. So this set has full measure. X. And so the last point is that the singular set stratifies just like the singular set of non-collapsed Ricci mid space in different stratum. So just like that. So in Richard Damer, so we call this certification. So singular sets. The Hausdorff dimension of the set SK, which is by definition the set where the set of points where you cannot find a tangent cone. So a tangent cone that splits K plus 1 in different lines. Okay, so the Hausdorff dimension of this set is bounded from above by K or in K. Okay. So, are there any questions?
Junior, je suis qui s'appelle Junior. Okay, okay. Sorry.
Yeah. Okay. Okay.
So people come with the microphone. They come in the story with their microphone.
Okay. No problem. Okay. So in the remaining time, I'd like to give some ideas on how we establish 2 points. So these points, the fact that tangent cone are RCD-0 spaces, because in fact this, and okay, the second point is the fact that any tangent cone of non-collapsed Kato limit is a metric measure cone. In fact, we will use the fact that the tangent cones are RCD-0N to somehow, to force them to be metric measure cone thanks to non-results in the RCD theory. Okay. So we start. Proof. With Carron and I. That will be very sketchy, but the main idea is the following. So you start, okay, so you take the points in this Kato limit. I take the tangent cone in this Kato limit, so I'm going to write it like this: Tx x, x, and the line x for the set, yeah. And for the point that will be the tip of. And so now you can write this tangent cone as a limit of manifolds whose Kato quantity, the kt, goes to 0 for any t. So let me make a picture and explain. So let me say that this is the first step. It's something quite common in the study of tangent cones of limit spaces. So you take your space x, you can approximate it with. So you approximate it by definition by with manifolds. Then you take your point x in x, and you rescale the space. Get the tangent space, the tangent cone. And now, so here you can just rescale the manifolds themselves in order to make them converge to the tangent cone. And the point is that, so if you, okay, so let me call this rescaling m alpha, epsilon alpha minus 1 j alpha, where epsilon alpha goes to 0. Okay? And now the thing is that kt of m alpha, epsilon alpha minus 1 j alpha, by rescaling properties of the heat semigroup, like the heat-kernel, so you write the heat semigroup with the heat-kernel, you have good rescaling properties of the heat-kernel, and so you can show that this writes as follows: k alpha squared t m alpha t alpha, and this, from your Kato assumption, this is controlled by f epsilon alpha squared t, and so this goes to 0 when alpha goes to 0. No, when alpha goes to infinity, sorry. So and you have this for any t. Okay, so your tangent cone is a limit of manifolds with kt converging to 0 for any t. And now step 2. So you take a given closed Riemannian manifold, you assume that the kt is small, okay, and you derive some analytic property, an inequality, that is going then to converge to a nice analytic inequality on the limit space. Let me write the details. So prove that if it's directly this way, kt of mj is lower than epsilon, or epsilon small, then here, so you have this inequality, so 1/2 of PS squared minus PSF squared greater than some constant depending on epsilon times the gradient of PSF squared plus expression of PSF squared by n. You have this for any H22 and any S between 0 and T, and in a suitable weak sense. Suitable weak sense is that you just multiply by test functions and integrate to. Sorry. Okay, and so you have this constant here, and the thing is that this constant goes to 0 as epsilon goes to close to 1. Sorry, as epsilon goes to 0. So please. 1, epsilon goes to 0. Okay, and now from okay, so what you want to do is to say, okay, my tangent cone Txx, okay, I obtain it as a limit of manifolds with kt going to 0. So my tangent cone should satisfy this property with a 1 here. Okay, so this is step 3. So just to ensure that deduce that X satisfies. So again,
Excuse me, David, there is a question in the chat
Yeah.
about the meaning of this inequality.
Okay, so maybe I should say right now. So if you change this, if you replace epsilon by 1, then you have so this is so-called Bacri-Ledoux estimates, and so it turns out that this estimates is equivalent to the RCD0n condition by a work by two works by Ambrosio Savary and Herbart-Couadage-Tourne. So the way we prove that the tangent cone is RCD0n is not by using optimal transportation, but really by using diffusion theory of Dirichlet forms, in fact. So we deduce that this satisfies we can write the same thing but without with the appropriate vocabulary. And so, as I said, this is the so-called Bacri-Ledoux estimate. Which is equivalent to the RCD0n condition.
The first reference is Ambrosio, Savary.
Yes,
right?
yes.
Okay, that's fine. That's fine.
That's fine.
Yes.
Okay. Okay, so this is the general picture of the proof. In particular, we don't. It seemed hard to pass to the limit the optimal transport condition of the optimal transport RCD0n condition, and working with a heat kernel, which is at the core of the Kato condition, we're able to derive some nice estimates on the heat kernel, play with it, and ensure convergence of the heat semigroup from the manifold M alpha to the tangent space Txx. And so now with this semigroup, we can take the definition of RCD0n space, which fits what we have on the space. Okay, and now, so I'd like to give ideas now of the proof of what was point 1 in the theorem 2. So the fact that tangent cones are metric measure cones. And there's a non-collapsed, sorry, my letters maybe, okay. And there's a non-collapsed strong assumption. Okay? Non-collapsed strong Kato limit. And so here, what we do is, yeah, I think yeah. Okay. So we introduce some almost monotone quantities. Okay, so we have an almost Bishop-Gromov inequality. So in the case of Ricci limit space, this almost Bishop-Gromov inequality is Bishop-Gromov inequality, which tells you that the ratio of the volume of a ball reduced R by Rn is monotone and increasing. And you use this fact to derive that tangent cones are metric cones. And here we don't have a monotone quantity. So, and then the monotone quantity, the Bishop-Gromov monotone quantity, so the VG, VR, R, N is not, is not directly related to the heat kernel. So the idea is to introduce a new monotone or almost monotone quantity built from the heat kernel and use the nice estimates that we have on the heat kernel and the nice convergence results to get monotone quantity in the limit space and get that it must have the structure of a metric measure cone. So let me write here the quantities that we use for this. So we introduce quantities. So okay, this is a quantity theta x s t as follows: 1 by 4 pi s n by 2 integral over x of exponential minus u t x y by 4s y, where this function u is related, is defined through a formula involving the heat kernel. So I will write the formula, it will become quite clear what the role of this u. So where u, so here, sorry, okay, s and t are x, and where u is defined by this formula. So the heat kernel of the space, so this is the heat kernel, and so you want this to be equal to 1 by exponential minus y. Okay, so if X were a Riemannian manifold, a smooth Riemannian manifold, then Variance formula tells us that this U converges to the distance squared between X and Y. So this is because the heat kernel on a Riemannian manifold is asymptotically, as time goes to 0, the Euclidean heat kernel. Okay, so let me write this fact. It's important to keep it in mind. So Variance formula. So if X is a manifold, Variance formula tells us that u t x y converges to v squared x y as t goes to 0. So locally uniformly. In fact, what we really want to get, the quantity that we really want to get is the quantity theta x S0, okay, which would be so if I put a 0 here, if I replace this utxy by the distance squared between x and y, what I get here is the integral of the Euclidean heat kernel of the space. Okay, Euclidean heat kernel, I mean, I just take the Gaussian and put d squared xy, where in the Gaussian, the Euclidean Gaussian, I have a norm of x minus 1 squared. Okay, let me write this. So set also, you write this as b theta x of s as so 1 by 4 pi s n by 2 integral of x of exponential minus d squared xy s d mu y. Okay, and so this is the limit when t goes to 0 of small theta x s. Okay, and now so we can describe more in detail the proof. Step 1 is just to observe that if this quantity is a constant, then the volume ratio in Bishop-Gromov theorem is constant. And this is just a simple computation with Cavalier's principle. And so step 1 is to prove that if big theta x is equal to constant, then the volume ratio, so mu r by so mu br. Okay, so yeah, in fact, this is a general fact. Mu br like is the constant, and then so we know that tangent cones are RCD Variance spaces, and so we can also show under the non-collapse strong assumption that they satisfy also a technical assumption in addition that weakly non-collapsed, there are weakly non-collapsed RCD Variance spaces. And on weakly non-collapsed RCD spaces, there is a famous result by De Filippis and GE, which said that if this is true, then the space is a metric measure cone with tip x. Okay, so the idea is to use De Filippis GE. To say that Cx is weakly collapsed. If Cx is RCD, can collapse RCD and then X is a metric measure cone. So maybe I should write this because to make things clearer. So you can define this theta and big theta on quite general metric measure spaces. So maybe here I should precise what I really have in mind is to consider the big theta of the tangent cone at the what would be the tip. So this is equivalent to this, and then takes a metric measure cone with tip. Okay. And yeah, just write the last point. Yeah, stop. So in order to prove this, we rely on the fact that there is a function f from 0, 1 to 0+infinity, such that f lambda goes to 1 as lambda goes to 0, and for any and any x in the Kato limit, then this function theta x lambda s lambda t times f lambda is monotone. And so in this way, since f lambda goes to 0, we are able to define the limit when lambda goes to 0 of this quantity. Okay, this is monotone, so we can consider the limit of this quantity as lambda goes to 0. And since f lambda goes to 1, this limit is equal to the limit of this guy when lambda goes to 0. Okay, so this tells us that this limit exists. And then we relate this limit with the theta x underline txx, and we show that this quantity, this function is homogeneous, and then we deduce that the big theta on the tangent cone is a constant. Okay. I stop here.
Thank you very much, David. The talk was very clear, and it's not so easy on the board actually because there are lots of constraints. So thank you. Are there questions? Oh, I see two hands raising.
Okay, I have one, David. So how strictly bigger the class is? I mean, this class of Kato. I understand the interest from an analytic point of view, but geometrically, yeah. I mean, simple examples that are not RCD spaces, which are Kato.
Yeah, so we are working on examples. So, so in fact, it's a very good question. It's not easy to construct explicit examples of a strong Kato limit, which is not a limit of Riemannian manifolds with an LP bound. Okay, so we have a gap between a lower bound of Ricci and LP bound on Ricci, but we still don't have a gap between a lower bound on Ricci and Kato. But yeah, but we have some plan to construct an example, and hopefully this time it will work.
Okay, thank you.
So I see hand raising was Gilles Courtois.
Actually, it was Alex has asked my question, so it's okay. Thank you.
Okay. Thank you. And Jason.
Yes. So since you have, like in your preprint, you have some nice Gaussian type bounds on the heat kernel. So if you view the the Kato constant as a type of as a sort of Green's kernel, since you're integrating the heat kernel over time and convoluting, can you say anything about the Green's function in the limit and what this says about the tangent cones? Like, can you get more information on the tangent cones by looking at this Green's kernel in the limit?
So on a fixed Riemannian manifold, you can also define a Kato constant with a Green kernel. And so if you integrate, if you let t go to infinity in the parabolic Kato constant, Kato quantity, then you get the same quantity, but with heat kernel integral between d1 and t of the heat kernel replaced by the green kernel.
Right.
And, on a Riemannian manifold, it's I mean both are I mean they are controlled one from the other, and so I don't know. So we prefer to use parabolic version because we had nice estimates on the heat kernel. So I have no idea on how to work with a Kato constant with the green kernel. I don't know.
But as I understand the question, also, is there any kind of heat kernel at the limit or green kernel at the limit in a reasonable sense?
You mean in a Kato limit?
Yes, in a Kato limit.
Yes, there is. Yes, there is a heat kernel in the Kato limit, and there is, and you have locally other continuous convergence of this heat kernel. This is contained in our first result about the Moscow convergence of the Dirichlet energies.
Okay, Gilles, your hand is raised.
Yeah. So, David, can you say a few words about the statement concerning the codimension of singular sets? Or?
So, probably what you have in mind is the statement that the singular set has codimension at least 2, right? Yeah. Okay. So with our tools we can prove it, and it is true. Just doing the same proof as Cheeger coding in the context of rich limit spaces, and so we have it. It's going to be in the second paper topic.
But how is it? How does it rely on this heat kernel condition? I mean,
so in fact we don't use it. I mean, as soon as you know that as soon as you know that your limit space behaves like a rich limit space, you can use some degree arguments used by Cheeger and coding on. In the context of rich limit spaces, you just apply the same argument and it works.
Okay, I see. Yeah. Thank you.
And there is a question by Andrea. Please, Andrea.
Yeah. Hi, David. Thanks for the very nice talk. A couple of questions. One is, can you make the Reifenberg-Cheeger coding machinery work also here? So say that the regular set is included in a topological manifold, because say from what you said, it seems so. So from what you said in the Blackboard.
Yeah. It's
okay.
Thing is a second paper.
Okay. Okay, so you're
it's something. In fact, as soon as we know that the structure of such a Kato limit space is it's very similar to rich limit spaces, just have to run the machinery of Cheeger and coding, and it works.
Yeah, thanks. And then the second question is, say for rich limits, you know that. You're also able to say something in case of collapsing volume, right? So how necessary is the volume non-collapsing in order to at least start to run some of the machinery? So I see that, say, a lot of the consequences are not are out of hope. Like, for instance, that the tangent cones are metric cones is hopeless for without lower bound on the volume. But say, can you at least start? I don't know. For instance, with do you have some local doubling, or it is, or really you stop from the beginning?
You have local doubling. I mean, if you rescale the measure and so you preserve the local doubling property. So when you rescale the measure, local doubling measure, it is still locally doubling. So you get from the limit space, you get that it is locally doubling. You also have the Poincare inequality. Okay. So even in the collapse case, you know that the space is doubling with Poincare. And then what kind of?
But for instance, what prevents you to do this argument that you sketched at the Blackboard that tangent cones are RCD? So because this characterization of RCD works well also in the collapsing case. So you don't need that you are top dimensional. So this characterization via the Bakri-Ledoux its semigroup works well also without assuming non-collapsing.
Yes, so yes, and but
so maybe next is an even other paper, so to consider that. But I think there could be something.
Yes. Yes. So the thing is that this Bakri-Ledoux, to get this Bakri-Ledoux, even in the collapse case, we get it with Bakri-Ledoux 0n because it comes from the sequence of n-dimensional Riemannian manifolds.
Yeah.
And even if they collapse, they satisfy the Bakri-Ledoux 0n, so almost Bakri-Ledoux 0n.
Yeah.
So if you converge, but you get this Bakri-Ledoux 0n. So you get RCD, and I don't know. Yeah, I have no idea how to catch the collapsing in the convergence of this Bakri-Ledoux estimate.
I don't know. I think there is no for that there is no hope, because also say if you have a collapsing limit of say of n-dimensional manifold which collapse to a k-dimensional manifold, then the limit is only RCD, say Kn. So you cannot improve you cannot lower the dimension of the n with dimension of the limit. So the best that you can hope to say is that the tangent cones are RCD 0 n, where n is the dimension of the starting sequence, not of the collapsing, not of the collapsed object. But still, then you can still do something. So, for instance, you can still hope to say that tangent cones are Euclidean almost everywhere.
Yes, you can also say that even in the collapse case, there are the regular sets are K, where the tangent cone that you see is RK. These are K rectifiable sets.
Yeah.
You can second paper.
So that's okay. That's future project. Good. Yeah. Thanks a lot. Yeah, very nice project and very nice talk.
Are there any other questions? Okay, if not, thank you very much for the talk, and we are waiting for the second and third paper. Thanks. Thank you, everybody, and in 25 minutes or a little bit less, we will have the very last talk of this summer school. Thanks a lot.